15 minutes with the question, more or less.
We'll let you know.
Goody. So I've been presented, so I don't have to do that. And this is deep learning, hence the brain. It has to do with auto-guided vehicles, and not little small mini robots, but big machinery like a tractor. And it's thermal imaging, so I have that there also. And to get the formalities right, this is done together with Samuel and Dana at VD Systems, which is the software package I'm using for processing it. So they have their logos, we have this conference, we have EU, FP7, and CIGR2016, they funded it. So the contents are pretty normal. The background, deep learning, what is it? And what is VD Systems' take on it? How is it trained? There's a guy who asked that every time, last sessions I've been in, so I'm going to show it. Application on thermal images and conclusions. So the data set I'm using for this needs some background because it's from another project, also CIGR, called QuadAV some years ago, where we were doing sensor fusion of many different sensors. My part of it was stereo vision with HDR images and a FLIR camera for thermal images, and then I would fuse those to detect traversability in front of a tractor by dividing the scenery into cells and making them red when there was an obstacle, based on the distribution of height values and and temperatures within that cell. I ended up with a long pipeline. This is one moving, it's supposed to move. Oh, that doesn't work, so that's annoying. So it would, you can see there the reference image in the cameras, and that's the thermography, because you can't really see much there because there's not much going on. And then in the middle is the cells. What is deep learning? It's not really new with neural networks. You usually have these multi-perception layers where you can then plug into the algorithm a list of numbers based on how many input neurons you have. One example here is a spectrum from a high-spectral sensor that then leads to an output image that will classify each pixel, and then you can run that on each pixel of the algorithm. And then you get some regions, for example, here Tetra Pak, milk cartons, juice cartons and such. And then you can sort that out, and then you can see the difference between just a cabbage box, which looks a little like it. It's a shiny carbon box also, but it can see the difference because of the hyperspectral data. So this is pretty typical working. It has to taste a little more of agriculture. Then I have this small project with Apple's Gap, where I used, here I didn't want to just base my decisions on one pixel because there's some texture I needed to see. In order to do that, then you have to start to use all your knowledge in machine vision, and then you can do, for example, texture laws. That then gives you this list of numbers for each pixel. But now you have some numbers that are based on the neighborhood also. And then you can segment that. And here I then found which leaves are in focus. So I can, within those leaves, find the dots, the spots on them, and then do that. That's a lot of work in finding out which algorithms to put together to do that. Then deep learning came around, and also existed for a long, long time, but without the processing power to do it, and the algorithms to train this complex neighborhood-based topology. So now it can actually learn to do those filters that I otherwise would have to do myself, and base the decisions on the neighborhood also, so it will learn what texture you are looking for also, and maybe even the surroundings of that texture. This figure is from the media, the SDK. So VD systems, what is they are doing? They have, it's based on a guy who is actually a neuroinformatics researcher from Zurich, who was, he wanted to base machine vision on how humans not only interpret images, but also how they recall images, so that it makes the tie between interpreting and also how to recall something that has already been learned. It can be used for positioning and inspection and classification. Positioning is to find a feature and track it. So it can also locate it in an image, pose, and find the pose of it, and the scale of it. When you have inspection, that's what we have seen a lot at the conference already, where you segment an image. Similar as I did with the multi-perceptron network with texture laws. And classification is the typical Google find dogs, dog images or cats and images, where it classifies the whole image. Then self-learning, of course. It has the GUI for doing the training, where you have to paint as a laborer's work. It has all the tools for analyzing the result also, rock charge and such things, recall, classification, and precision and classification. It has been optimized and pre-trained, so it doesn't take many hours to train it. You're usually around 10 minutes of training time. On a desktop computer on my laptop, it's more like 20 minutes. But it's also very fast. Once you've trained it, it's often deterministic except for the positioning tool. Because the positioning first have to find candidates and then classify them. So there it depends on how many potential features there are. What's this one? This is from the GUI, the same example that I had from Helcom. This is quick time time is not available, so it will not be able to show it anyway. So what it does here is that that's annoying. Yes, I have to put those on, and people interested can go and see them there, or you can download the presentation or something. So here I will show how to, I would like draw on top of all the features it had to detect. And then I would draw these 4 up here, and then the last 2 I would mark as good, that's why they're green. Then you can see out here, we have all these different permutations that we can do on images, change the contrast and scale it and rotate it and do all those permutations on these images. And then you could train it, and then it took about 20 minutes, of course skipped that. And then it would actually detect all the scab spots on these ones. Then I noted afterwards that this one actually did have some, but then the rock chart would have a threshold I could move, and then if I moved it a bit further down, then it would start to also detect them on this one. You just have to take my word for it so you can see it. So the experiment that I then decided to do was, with the thermal images, would it be possible to process thermal images alone at a guaranteed frame rate. And I took about 2,000 of my thermal images from the old experiment. And I've defined classes ground, grass, bush, maize, tree, and critical. Critical was humans, animals, vehicles, and buildings. And then also I had issues in the old project detecting the lakes, so I tried that one too. Of course that would be critical too. But it's critical in a different way. It's more like a negative obstacle, while the others are what we call positive, sticking up. So I used this segmentation tool in VD for seeing if I could just find these critical obstacles with that and have it mark them. And the green tool for classification, where it was the whole image. And I did this on a GTX 980 Ti. So, these are examples of the different classes, and I don't know if the contrast in here is good enough for that, especially with the light on. But see for yourself, you can see what is what here, and now I press the button and we jump in, and you get it right. So we have the bush and the critical and the grass. Grass looks kind of funny. We have the tree up there in the corner, and we have a maize there. That's pretty easy to see, especially on the my screen. And ground, and the lake. Here you can see ground, what is ground? There's maybe always a bit of grass on the ground. And what happens when you approach something from ground or grass to a bush or a tree. So when you label this as the human, then you are a bit subjective there also, so you cannot really expect to get 100% accuracy of a classifier. Because it might, the limit when you approach something might change. When you train the network, it will cut the cake differently than you would. But it works fine. This is segmentation, where you have a human human hiding inside the crops there. And here we have, in the second one, we have a human and then the lake in the background. And then we have a tree and a human. Now we're going to also see an issue with classifying the whole image on the next slide, but there's actually multiple classes in the image. Here we have the rock charge. The list operation is pretty good. Processing time is 25 milliseconds, and it took 25 minutes of training. But hours of labeling this, you have to sit and paint. 2,000 images, that's a lot. Do training, good. Training on 600 of those. For the classification, we have this confusion matrix. You see it's often like the ground and the grass is a lot, and that's obvious, and bush and tall grass, again, you're moving from something into something a bit higher. When do you cut the cake? But here it was 8 milliseconds processing time, so that's extremely fast. You can basically just snap an image and run it. This works. So again, we'll have to upload these videos so they can be seen. Those looked amazing. So, the computer is feasible to do this thermography. Here we have some limitations in the way the training was done, even though we trained on so few samples. And it already works very well. It's still the same situations we are evaluating on. We're not transferring the training of the trees to other situations with other trees. So we need to do that in future research. And we have to research what happens with the thermography in different weather conditions. And what happens when you go from the cold night into the warmer day. When you work with thermography, there are some hysteresis. We have to research how the training can transfer for that, or we have to train in all those situations, or we can use weather data to actually predict how the thermal images are going to change and then compensate for that. So, that was it.
So if there are any questions? Yeah?
I'm Victor Canatis from Air Israel. My question is, what type of data did you use to train and predict? Was it grayscale 8-bit images or the raw temperatures of the camera?
With images like this one, I did a pre-scaling but a fixed scale to I could actually take the 16-bit images and plug in, and the algorithm wouldn't care, but I would not be able to see what's going on. I wouldn't be able to draw my paint on it. So therefore I did a scaling that gave me enough contrast to actually work with them. But I did the same scale factors on the entire set.
Was the scale constant?
Yes, something. I also tried, the first training I did was to take an auto-scaled set, but then the training was horrible. So I decided to do this fixed scale. Yeah.
Did you use a pre-training network or did you train it?
Yeah, Suite uses pre-training. That's why it's so fast to get it to converge after that. And they also, Dana was involved also because I needed a bigger network under the hood, which you don't get access to. You do in the unsupervised mode, you can choose complexity of the network from small to huge, they call it actually. And I needed it extra huge.
Is it possible to estimate the distance from the obstacle, or you just?
Then you need the more complicated stereo algorithm with it.
Is it possible to combine this technique with the cameras, time-of-flight cameras, or Lidar? So
yeah,
I
don't like time-of-flight. They're really horrible to work with so far that I've seen. Maybe the new Basler camera will be better, but we did a few experiments with it, and that seemed to have the same issues that all the other one has. So, Lidar would be probably better now. You can get these extremely fast rotating ones that the guy out there has to play with.
Sorry, also a question. What is the maximum speed that you can imagine a vehicle can run?
Vehicle computer stations with 25 milliseconds, if you're going 10 kilometers per hour, then that's actually already 70 centimeters. But the 8 milliseconds would like 40 centimeters, and I don't know how fast a tractor can actually brake. But then the milliseconds here adds to the braking length. So.
Okay, such speed vibration are not a problem for the camera.
That's why I'll put so many videos in, so you could see how convincing it is when you see it moving. But apparently it requires quick time on the computer and it's not installed.
Okay, thank you.
Thank you.